we were considering the delta learning rule as an example to understand the various parameters associated with the convolutional neural network, right? And our intention now is to understand the whole concept of weight update by looking at various schemes. Out of these schemes, the names we already have come across maybe several times in the previous lectures, but we never went inside to understand what exactly is happening. Okay, so our idea now is to understand them in detail. So the first thing is the SGD, which is nothing but the stochastic gradient descent. So why it is called as a stochastic and what the descent stands for. We are going to see that now. Okay, so consider the stochastic gradient descent. Now, it's the most simplest method actually, right? I give one training data at a time for the machine to learn. What machine performs, in a sense, strictly talking about the neural networks. It takes an input, right? Multiplies that with the weight. Maybe if there is a bias, it adds a bias, gets an output, takes an activation function on that, and provides an output. So that output is compared with the desired value or a target value. If it matches, no problem, right? No need to update the weight. If it is not, if there is an error, right? If the output is not matching with the desired, right? Apply a learning rule. Again, under this condition, the learning rule which we are using is the delta. So you calculate a delta, alpha into delta into the error, not error, it's x value, alpha into delta into x value, x is the input, right, will give you the change in the weight required, right? So that delta w you apply to the old value of w, right, to get a new value. This is what is the in general, this is how the weight updation happens. Okay, now the stochastic gradient descent is a technique which calculates the error every time you train, right? So the schemes are like this. You don't have to calculate the error every time, right? There is no rule saying that every time you train, every time you calculate error, and every time you update. This is not required. So, but since the stochastic gradient descent is the most basic and the oldest technique of learning, right? Making the machine to learn, right? You can see there is a tag, right? I have so many data, training data. So I give the data in what fashion? I'll give the data one by one. So whenever I am giving the data one by one, right, every time you give the data, you update the weight, calculate the error and update the weight by doing a training. So fundamentally, the training happens every time you give the data. This is pretty simple, actually, right? Nothing but other. So equations we already have, right? What is the equation for weight update? Wij is equal to Wij plus, right, delta Wij. So that is there. We cannot change because that comes from the specific learning rule. But then what is this stochastic gradient descent? That complicated term like stochastic gradient descent, right? What is that? Now, understand the training happens every time I give the data. Every time this is what we have understood so far, right? We never knew that, okay, we can even change that, right? Training, it's not necessary that I should train the machine every time I give an input. What are the other options? We'll see later, okay? Batch and mini batch, etc. are there, right? We'll see the differences at a later stage. But now you understand that this is the simplest one, what we were already doing, right? That itself is the SGD technique, right? Now, in such case, why such a complicated name given over there, right? You see, stochastic actually comes from the statistical part. Whenever there is a, so you are conducting an experiment, and if the results of that experiment is, if anything can happen, like you may get, you may win, you may lose, something like that. So, right, that kind of randomness is there. Weights may increase, weights may decrease randomly depending upon what is your current input. So you can see here, I'm talking about this particular equation specifically. So you see here, right? change in the weight is equal to alpha, right? Learning rate. Delta value is how we calculate differentiation of the activation function into the error. Right. Now you see the error can be positive or negative when you subtract it, right? The desired value minus your target value. When you subtract, it may be positive, it may be negative, right? There is a lot of things that can happen. It can take any value. Stochastically speaking, right? It can be right a random thing. So again, this input data, right? That also depends on actually matters while we calculate the change in the weights. So because of all such parameters, there is a lot of randomness present over there. That's why the word stochastic comes into picture, right? Gradient descent talks about, right, how the weight comes to the minimum, right? Our ultimate goal here is to minimize the weight, not the weight, sorry, minimize the error. So this error should be minimum, means there should be no weight update. So this delta W should be minimized ultimately. So error reduces, delta reduces, this delta Wi reduces, correct? So that means the weight update, right, is not necessary. So ultimately the decrease, right, decrease in the error value is the ultimate thing. So you as per the definition which we have used now, if you are using 100 training data, right, I have to update the weight for each and every input I give. For every input, calculate the y, calculate the error, right? If there is error, update. If there is no error, don't update. This thing should, this, if you are trying to write this in a loop should run so many times. Okay, pretty simple definition. I think things are very clear to you now, right? So I would like to know if there is any doubt in this concept, only the SGD part. Okay, please let me know if you have any doubt. Otherwise, I'll proceed further. All right, then I would like to move further. So this is the batch method, right? So the batch method, like instead of giving a input, training and observing the output and updating the weights for every input, right? You wait until the complete data set is given once. I have, say, maybe I'll go for a simple example. I have 10 data. Okay, in a class, I have 10 different data, right? For every input, I don't update. I wait for the all the 10 data should be given to the machine. I'll try to save the answers the machine gives every time. It can be right answer, wrong answer, doesn't matter. Or you can also save the errors, because instead of storing the exact values, you can store the errors. Okay, and at the end of all that data set, training is over, you do something related to that. Maybe you can take the average of the error to decide whether weight should be increased, decreased, or something like that. Use that as your error value. Calculate the delta value from that. Use that delta value to calculate delta W, change in the weight, and use that further for the weight application. This is, you see, calculations are less here. You don't have to do all the calculation. This still works. I'm going to justify both cases. We are going to write a code from scratch for SGD as well as this technique, and I'm also going to make a comparison ultimately at the end. Okay, so let's see that. I'll try to give a diagram as well, so that we can refer to this just to remember what exactly each of them are doing, right? So just look at this. So this is a batch process, right? So weight updation or the updation happens, right, for one complete set of training data. Right? Now there is a question, okay, if at all after all the 10 I train, and if the training is not enough, what do you do, right? So in such case, we have what is called as repeat the whole training data set once again. We call it as a epoch. I'm going to use the word, I'm going to bring the word at a later stage. But since definitely few of you may have that question, right? So that's why I'm trying to answer that now. So since you are not training at every instant, right? Every instant of the input data, you will do that all at once. So now let's say, right, you do a validation as well. You find that, okay, machine has not learned. then what is the solution? You give the whole data set once again, right? And at the end of that, you do it. So data set may be same. Normally we shuffle in the when I give it for the second time, right? I will not give the data set in the same order. I will shuffle them so that there is a some kind of right. You try to make it random. Randomly you shuffle them so that machine learns something, right? So this has been a proved method. So whenever you have a huge amount of data set, every time you should not make the machine to learn. Weight updation every time means it's going to take a lot of time. So right, you try to reduce the number of calculations or weight update, right? Okay, so that's what is going to happen here, right? This is the whole data set, right? As I just mentioned, give everything as your input, right? And at the end, take the average of the error possibly, right, to use that as the parameter to update the weights. Okay, so that is the second scheme which we are talking about. So the equations is you can see the equation over here, right? It's see there is a 1 by n where capital N is the number of the samples present in the data set, right? So every time you may calculate, so there are various approaches even inside this batch. I'll tell the alternative option. Maybe we'll use that for our coding as well. So instead of calculating the error, right, and keeping saving the error every time you calculate what's the weight that needs to be updated. Okay, weight change in weight you calculate, but don't update the weight. Calculate delta W1, delta W2, delta W3, up to delta Wn. N samples are given. N times I calculate these values. Okay, delta. At the end, use this particular equation which we see here. It says that calculate the delta W values, right? Every time, take a sum of them. Sum divided by the total number is nothing but F. So whatever is the weight update that is supposed to happen every time, I don't do that. I save them somewhere and I keep adding them. And at the end, I divide by the total number of samples I use so that I get an average weight update. So that's what has been shown over here. So, right, both the methods we discussed are approximately going to generate the same this thing, right? One of them will do now. Other one you can take it as a homework and you can try to write that particular code by yourself. Right? Okay. And then I'll move further. I'll move ahead to the next concept that we discussed so far. It's called as a mini batch. Okay. So you see, this is a mini batch concept. All right. Here, you will further divide. Right? You will not the average of weight will be taken for a particular number of trainings, right? In this case, you can see we may have 10 individual data sets for a class, but I want to apply the batch method only, but I don't want to wait for all the data set to be completed during the training process. So what you can do, you can see that we will pick an like maybe every 3 inputs, right? We try to take an average and we update. You don't have to wait for the complete process. This is the difference. You call that size as the mini batch size. All right. So total data set is 10. I update the weights every 3. You can call it as the iteration actually, right? Because three individual data will go, right? Get a weight, accumulate the weight, take the average, and update. Next 3 once again. After that, another 3 will come once again, like that. It repeats. Okay. So this approach, if you use, then that is what is called mini batch, right? Nowadays, right, mini batch is also being used widely. Okay, fine. But the difference is just like that. First technique, SGD, individually, every time you update. Second thing, take the whole data set at once, keep calculating the weights, update the value that needs to be updated, but you don't update for them until and unless you finish the whole data set. Take the average of that weight value and update. Okay, so the third option is mini batch, wherein what we do, we pick a number, right, which is smaller than the data set size. Data set size is 10. I pick 3, 4, 5, whatever. Okay, so after that many training samples, right, I update the weight by taking the average of only those weights to be updated. Okay, so that's the fundamental difference. All right. Okay, now I'll try to define the very important word which is called as the epoch. Right, as we know now, the epoch is defined as the number of training cycles of the neural network, right? Number of training cycles. In a sense, once you give the complete data set to a machine for learning, that says it is one epoch. All right. So the number of epochs, right, are going to be, right, you can define the epochs that's going to take place depending upon how you are trying to give, what scheme you are going to follow. All right. But anyway, so that discussion will keep for some other day. Let me directly show you one particular diagram which talks about the whole, the complete thing which we are supposed to discuss, right? So this is the one. You see that training data is there, right? I give the complete data set. How do you update the weight? Doesn't matter. You update part by part, single every time, like SGD or a batch or mini batch, doesn't matter. Once the complete data set is over, you call that as one. So that's the ultimate thing, right? We'll define the epochs, right, for the same purpose when we write the codes. Okay, so now we'll move on to the example part where we are going to write the codes. All right, let me.
Excuse me, sir.
Yes.
Excuse me, sir.
Yes, please.
So what is the concept of learning rate? I mean, how to decide the learning rate?
Okay.
Generally, we consider 0.01 in our programs.
Okay. Okay. See, the learning rate has it's something like how quickly you want the machine to learn. Okay, so that's the idea, right? And it in my experience, it depends on the data set. Okay, if the data set is easier, smaller data set, like the one which we are going to use now, see, I'm not going to keep that value closer to 0.01 or 0.1, because if that is the case, though my data set is very simple, right, it's going to take a lot of time. I don't want that, because I'm very sure that my data set is very simple. In such cases, you can give even the larger one, like more than 0.5, 0.6, 0.7, 0.8, even 0.9. I'll show you that. Okay, that's one thing. So depends on you. You will be able to decide that based on the idea you have on the data set. Simple data set, right? The one which we are going to use now is such example. I'll show you, right? We'll keep higher value of alpha and still machine learns. Okay, when you have a huge data set, varieties of data present inside that, and the number of data you have is too huge, right? And maybe the parameters machine has to learn are many. Okay, in such case, you need to give time for machine to learn, so that you need more and more epochs, right? More and more learning. That means learning rate should be kept as small as possible, like 0.1, 0.05 will work. Okay, but that means you should be ready for longer duration of training, right? Maybe the epochs should be maybe 1 lakh, okay, with huge data set, not a small data set. So even when I'm giving to use the smaller data set now, maybe I'll use a epochs or the number of times the loop is going to run. Maybe I'll keep it as 5,000, 10,000, whatever. Okay, but you see, when the data set is huge and there is a lot of variety means there is a lot of parameters to be learned by the machine. You have to give time, so that you don't expect machine to learn quickly. Don't keep that value higher, you keep it smaller. But fundamentally, this is what I'm telling from my experience. Okay, various projects, when I did, I could learn this. But the point is that there is no fixed rule saying that okay, you have to keep only this value, right? But as I mentioned, I could observe that, right, data set is simple. You give alpha as normally, as you mentioned, you may say that okay, there is a rule saying that we should keep it as small as possible. Yes, that is going to work. For a simpler data set also, you keep alpha smaller, it takes more time, right? But machine can learn it quickly because data set is simple. You may have to give more iterations, that's fine. Keep alpha as 0.7, right? Give 10,000 iterations. It will do that job, and learning will be very quick. Okay, so there is a small part of trial and error as well, right? Only from practice this comes into picture. But since you asked the question, I try to answer.
Okay, sir. And this learning rate is fixed. I mean,
Yeah,
throughout the entire
yes,
process, for
for
a
one
process.
algorithm, when you write an algorithm, right, you keep this alpha fixed. So when it runs, right, you normally this is fixed. But nowadays, what happens, I'll tell you. So we have
Okay.
some of the functions inbuilt, maybe inside the TensorFlow, inside the Keras, etc., where you can actually specify. You learn something, machine learns something. You can specify at what point of time after. Let's say I define one lakh iteration, right? My loop runs one lakh time. I can say that, okay, after 50,000, change the learning rate by this much, right? You may reduce, you may increase, depends on your requirement. That is also there, but I cannot keep changing continuously. At a point, I can define. All right. So after so many iterations, change this. Once you can do throughout in your whole process. This is allowed. Okay. So some functions are there where we can use it, right? So
Okay, sir.
right.
Okay.
So that feature is also there, right? Okay. Any other question? All right. So let me try to define a problem now, and we'll try to answer that problem. Okay. So the problem that I'm going to define now is first we'll try to solve a simple classification problem. It's a binary data only, and let me show you that. Okay. So this is my problem, right? I have a training data. Now, previously we discussed that if it is a if it is a supervised learning, I prefer writing it in the specific format. I have a data set and a class. So you can see that the training data set, we have only 4 data sets. Very simple. Maybe this looks like a gate itself. Some logical gate we are trying to implement. Okay, maybe. Fine. Now you see the first 3 points, right, in that particular data set format. First 3 are the actual data, right? And the last one is the class. Class is actually, if you see, it's like it's a thicker, it's a bold letter. So first 2 data, 001 and 011, they belong to class 0. Okay, and 101 and 111, they belong to class 1. Right. So now my intention is not to go for a complex algorithm and do the programming by using some built-in functions. No. Okay. So that's not my approach here. I want you to know what exactly this SGD performs inside. Right. I can call it inbuilt function which does this job in a fraction of time and I'll get answer. That's not a case. Right. So in order to understand, right, I don't want to go for more layers. So I'm not directly discussing the deep learning related topic here. Let's keep it simple. Let's keep it a single neuron first. So in this case, you see how many inputs are there. The first 3 bits are the inputs, right? So I'm going to use 3 input neurons. Okay, there is one neuron that itself is going to provide the output because I have only binary classification. Maybe this y can be 1 or 0. Depending on that, I can classify. So there are 3 weights to be used, right? So fundamentally, so far whatever we discussed, right, I'm trying to write the same equations over here. So no change in the equation because I'm still going to stick to the delta learning rule itself. So equations corresponding to delta learning rule you can see over. All right. Okay. So uh, we need to define something, activation function, what you are going to use. Let's fix that. So already we discussed sigmoid. I'll keep the sigmoid. This particular layer, output layer, is going to activate its value depending upon the sigmoid. All right. So the architecture is fine, right? It's very simple, right? So once we know how to write a code for this from scratch, right? We understand that okay, this is what is going to happen. So I can jump into I can see what built-in function can do the same job and how to do that. It's fine. Various parameters present inside that standard function or built-in function, we will never understand if we don't go to this level. Okay, when we learn things, initially we need to go from scratch. Later on, we can directly jump onto the advanced topics. Okay, so that's my objective. So first, let me define the activation function itself. So I'll uh, define the okay, I'll call it as a my sigmoid function. All right, I'll pass a variable x to that, right? And maybe I just have to return a value. written simply, it's 1 divided by, if you look at the equation, I'm simply trying to write the same thing here. 1 plus x, okay, sorry, exp does not exist directly. I should write np dot exist, right? Okay, np dot exp of minus x. All right, so let me run this and go to the next session. And now my objective is that I simply want to write a function, right, that takes the weight. It should also take the input and the desired values. 3 values it should take, because in order to do the weight upgradation, right, using a specific method, these are the 3 fundamental parameters that needs to be passed to the machine. So neural network design happens over here now in this part of the code. Okay, again I'll define this as a function. Okay, because I'm going to call this again and again, right? If I sorry, if I want to iterate 1000 times, that means 1000 times you are calling this function. So writing a function itself is the easiest way. All right, so define. Let me call this as, I'm using the delta rule, right? But the weight updation happens according to a scheme. Let's call that scheme as SGD, right? So the name will suggest you, when you read this, you understand. Okay, so I'm using the delta learning rule for weight updation, but the scheme I choose is SG. I'm not using batch or any other. Okay, so just now we mentioned it has to take 3 inputs. All right, so first one I'll call it as a weight vector denoted by W, and say input, I'll call it as X, and I have a desired value. Okay, so these are the 3 things I'm going to use as input. Right, now you see, this is the point where I mentioned that alpha can be kept higher towards the higher side as well. See, this data set is pretty simple, right? Only like 2 classes, only 4 data. There is nothing, in the sense, no complicated pattern to be recognized by the machine. Okay, some very simple case is this. So when you go for that, I can define the alpha equal to, now you see, I'll try to keep larger value. Let's see, I have not tried with 0.9, but right, I already told you that this is a simple case. So even if you keep a higher value, it should work. That's what I told, right? So I'll try to justify that. Okay, I'll keep it at 0.9. Let's check what's going to happen. Okay, and I'll use a number n just to say that this n holds the number of classes in that data. Okay, in this particular code, we expect that. Otherwise, definitely number of, we can see the X, capital X, and we can see inside how many rows you have. You can extract from there. Okay, I don't want to go to that level because I'm very confirmed. I'm confirmed with the concept that I have only 4 data. Okay, 4 data points. So I'll keep this n equal to 4. All right, so I think I have the data required for this. Now I can actually, for all such 4 different data points that are given as input, I should do something. For all the 4, what do you do? Right, calculate an output, right? Give this as input, multiply by weights, right? If you have a bias, add a bias. Calculate a partial output, right? That partial output, you give it to the activation function, get an output, take a difference, right, with the desired value, and if there is error, apply the delta learning rule and update. This is the whole concept, right? So now for all those 4 data points, I should do this. So that means I am very confirmed that I have to do this job 4 times. So go for a for loop. If you are not confirmed, if you don't have a confirmation about how many times you should repeat this loop, right, then a while loop is suitable. Okay, so since I'm very sure that I have to go for this loop 4 times, I'll go with for, say, I in a range. How many times? Its range is n itself, right? Because 4 is the range, 0, 1, 2, 3, 5. Right, so right, so for this range, now you see the capital X, right? Assume I'm completely passing the data set to the machine, right? Complete data set in the sense, you can see over here, right? This is my whole data set. It's a matrix, 4 rows, 4 columns, possibly. Or maybe let's say I'll bifurcate. My X is only 3 columns because the last column is the class. So that is a desired data, right? I'll give it separately, let's assume, right? So my capital X consists of the 3 columns and 4 rows, out of which when I try to give an input for the first time, right, or input for each loop, it's only one row, correct? That is one input. This is the output. Next row, next output, desired output, like that. So I should pass only a specific row. So what I do, I'll extract. So this is my objective now. I'll call it as a small x. Small x is equal to capital X of, right? Take the kth row, because k starts, is it k or something? My mistake, sorry, I didn't see. It's I, right? Okay, sorry. It's I, right? X of I, comma, all columns. I is 0, right? So I0 means 0th row will be taken, all the column. That is your input for the time being. So that's what is the meaning of this. I hope this is clear, right? Then I also have to take only one value from my desired matrix. What is the desired matrix? It's the last column or the bold values. Again, I'm going to put them as a completely single matrix, out of which I should take one by one, right? So that's what I'm going to do now. So let me write that as the desired value, individual desired value, small d. So capital D is my complete matrix. So from the complete matrix, you pick up only the ith element. Okay, 0 means d of 0, d of 1, d of 2, d of 3. So when you have a single value, whether it is row wise or column wise, machine understands. 0th element is the first element, right? Next element is always d of 1. Okay, whether you write in a row or column. Okay, so that's why I'm still able to write d of I itself for this. Okay, now x is there, d is there, right? So I already have a weight with me, right? Can I get the weight into x done, right? It can be done, right? So let me try to call that product, okay, added value v. Okay, so v is equal to, I'm going to use an np dot matmul function. This is because only when the matrix sizes do match, number of elements in W and number of elements in X, they match, you can multiply. Okay, it's a row matrix versus a column matrix to get a single answer. So matmul np dot matmul W comma small x. So you see W will have, right, so many elements, right? You can see the, okay, W is not defined yet, but definitely this has to be matched. Okay, only when this is matched we get the answer. All right, so any changes here when once we run the actual code, we'll be able to understand, right, if there is any mistake. Now we are thinking about what we are supposed to do and we are writing the code. Okay, so I got a v, this is a partial output. You have a partial value which is w into x. Summation of w to x is done here, right? After that, you should pass this to the activation function to get a, that's the actual output. So I'll call that as y. Okay, so y is equal to, we wrote a function, simply call it, okay, my sigmoid of this v. I got a value v, partial output, pass it through a sigmoid function, you get an output. Okay, so we have a y with us. So referring to our diagram which we had written here, you see I got a y now, right? Compare it with the d to get an error. Okay, use that error to update. That's the whole process, right? Okay, so we are still under the for loop only. So our next objective is to do this, right? I'll call error as e is equal to desired minus this y. Okay, d is already there, we have a d with us, from that I will subtract y. Okay, now go to the delta value. Okay, just now I wrote here, right? So first objective is to calculate this delta value. This delta is nothing but, right, we have the value, right, that is phi of v, right? Phi of v is nothing but that activation function's output, which is y itself. Y is equal to phi of v, right? So I don't have to write a phi of v once again. I can simply call it as y. Y into 1 minus y into the error. All right, so that's what I'm going to write next. So let me call that as a delta. All right, so delta is equal to y into 1 minus y, because phi of v into 1 minus phi of v. Phi of v itself is y. All right, so multiply that with the e. Okay, So this is going to be a single point. It's something like a scalar. Only one value you get. All right. So that's the delta term. Use this delta term to calculate this delta W, right? Which is alpha into delta into xj. So how should I write that? I can simply write. Let me give a notation. So dw. All right. So dw is equal to alpha, okay, multiplied by the delta we calculated, and multiplied that with the input. Okay, so you see x comes over there. X is nothing but the input. So currently whatever input you had given, for which machine didn't learn properly, machine made an error, right? That input also should be considered for the weight of it. That's why the delta rule takes care of the input as well. Okay, so I got this. Next is nothing but simply do this. That is weight is equal to weight plus equal to weight is equal to weight plus that dw. So all right, so that for loop runs how many times? 4 times. For all the inputs, this will run. Okay, and once that is finished, I can now return what is the learned values. It's a weight only. I don't want anything else to be returned. So simply return w. Okay, so try to write a very simple and a compact code that actually implements everything that is present in those three equations, right, which we see on the screen. Okay, is there any doubt? I can clear if there is any doubt over here. Please let me know. Meanwhile, I'll try to run this. Okay, as of now it says no error, but only when the value goes in, right, if there is any error, we'll come to it. Okay, as of now always it says there will be no error. Okay? Unless and until we have some errors related to the typing or any functions which we have misplaced. Other than that, normally we don't get any error over here. But that doesn't mean that the code is right. All right. Okay, let me go ahead and let's try to give the values now. All right. So all the values which we had shown here, right, I have to enter them now. Okay. So I'll enter two matrices, one for the actual data, the first three values 4 times, and one more matrix that takes the column. All right, the last column as input. Okay, so let me define this. Capital X is equal to np dot, I'll define this as an np array because it's going to be a multi-dimensional. So row wise I prefer entering. First data set is 0 comma 0 comma 1. Okay, and the second data is 0 comma 1 comma 1, and the next data is 1 comma 0 comma 1, and the last one is 1 comma 1 comma 1. Okay, that's the x. I'll also define my desired values. All right, so desired value is equal to np dot, it's also going to be an np array only. Okay, but I'll try to make it a one-dimensional case, right? I'll write row wise and take a transpose so that it becomes a vertical. All right, so that can be also be done, or you can even enter column row wise. I think this is the easiest one, right? 0, first two classes were 0 0, next two classes were 1 1, but this makes a row wise. I'll try to make it take a transpose. Okay, so that will do the job. You see, other than this, if you look at the preliminary requirements of the training or training a neural network, I need to define, initialize the weights also. So what you can do, you can give 3 numbers you enter, right? But if you try to make it random, that's more effective. All right, so I'll try to do that. So since we already have the numpy already present in the system, right, which is already loaded to the memory, I prefer using maybe np dot random rand. So I create random numbers. How many? 3 I need. So 1 rows, maybe 3 columns. I'll try to make it more random, maybe by just only this is sufficient, but I have it. Normally, whenever I write code, I try to make it something more random. I try to bring some more randomness into picture by just doing something like this. Okay, 3 times that random numbers minus 2, like, or 1.5 times the random number minus something. You can do something like that. That's another way. This is like randomness into some more randomness. 3 times that number is more randomness, and minus 2 is also a different data. Okay, so it's something like that. Okay, it's left to you. You can do whatever you prefer. All right, so this is the initial weights. I want to see what is my initial weight, and after training I also want to observe that my weights are changed. Okay, so for that purpose, what I'm going to do, I'll do a print here. I'll do a print statement. Okay, so print initial uh, initial weights. All right, equal to, let me do a plus here and string the values of the W. Okay, so this means we will be able to visualize, we should be able to visualize the weights which with which it initialized, right? I am expecting positive and as well as negative numbers, right? Because the rand function will create in that order. Okay, so that's one thing. I define that. Now I have everything ready to call this particular function. You see, I can call a function W if you have W, X, and D with you, right? I have them, right? You can see here X is defined, D is defined, as well as the W is defined, right? I can call it now. So you decide how many times you want to give that 4 numbers, right? 4 rows of your data set. How many times you want to give? What do you call it? It's epoch, right? So let's do that. So for, it's left to me, right? I can decide, right? You can start with a moderate number, right? Irrespective of the complexity of the problem, right? I prefer anywhere around 5,000, because 5,000 iterations for this small data set is nothing for our machines. Okay, our CPUs will do it very quickly, right? Maybe 2-3 seconds maximum. Within that, 5 to 10,000 iterations will be done. So it's not a computation burden for these kind of machines, right? Plus, if you are using GPU, then definitely go for 50,000. No problem, right? Quickly it will do, right? So for epoch equal to, not equal, sorry, my mistake. Epoch in the range, I'll keep, say, let's do a trial and error. If machine, I'm sure machine will learn for this number, but if at all it will not learn, because I kept the alpha high, right? Maybe that is also a factor over here. If at all it does not learn, I'll make it 20,000 at a later stage. Okay, so let me see what's going to happen. So for epoch in range, this number, so updated weight is W. W is equal to, call the function. What was the name? Sorry, I missed. Delta SGD. Okay, I think it should suggest, yes, delta SGD. Pass the parameters in the same order. We first should pass the W, then X, then D. Since we are giving the same name, no confusion. W, X, D. I'll pass it. So this means 10,000 times the 4 data, whatever we have, will be passed to the machine, and machine will learn. Okay, fine. That is done. Let's say this works fine without any error in the previous cell. If that runs, now you see I have to perform what is called as a testing, right? So training is over, weight gets updated. Testing, in the sense, I should give these 4 data once again to the same machine with the updated weights, and result should match my D vector, which is the desired. Right? That's the ultimate thing. Right? So training is over. We already have written the function, so it will take care of the whole training. So now in this part, do we have n? No, we don't have n. So I'll define n here, n equal to, say, 4. Okay, and I'll say that my output comes, to store the output, I'll create this. Okay, then for I in the range, right, range n itself. Okay, I in the range n, right? So 0, 1, 2, 3. So 4 times my data sets will go to this. Take out again, X is there. Take 1 by 1 X from that. So X equal to So some part of the code will be repeated here, okay, because our objective still remains same. Okay, this of say I comma all the columns, I'll take it, and okay, let me just see. Then once I have this x with me, I can multiply that x with the updated weights to get a partial output. So v will be the next step. Okay, so v is equal to np dot matmul, right? So multiply the weight. Now you see this w is nothing but it's an updated weight. That's what I'm expecting. W comma x. All right. So I got this, and my y is equal to every time I get a y, every y I'll concatenate with the empty list which I have created earlier. So I should use np dot, I think I can use concatenate, I guess. Yeah, it's there. Concatenate. Check your past value of y. With that, activated value of v should be added to this y, right? So I can call it as a maybe my sigmoid of v. So v will go to the sigmoid function, some value it will give. That value I'm concatenating with the y. So it's by default it will do a vertical concatenation. So if any doubt you have, you refer the concatenate functions help. All right. So you'll come to know. Default is vertical concatenation. So y is there. New value get below that. So next value will come below that. So I get a final column matrix. This is what I'm expecting. Let's see. All right. So I think this should run for 4 times, and once it is done, I should be able to print the one. Okay, let's quickly go through the code once again just to make sure that we are fine with that. Okay, so first part, what you are doing? Okay, you are defining alpha n, the range. Okay, x then d, v is equal to multiplication, y is equal to sigma, calculate error, delta. Okay, from the delta calculate dw, from the dw update the weight. So this is going to happen 4 times, right, inside this function, and I'm calling that function 10,000 times. Okay, it looks like others are fine for me. Right, let me quickly run through this. Oh, it's running good. Okay, I never I wanted one more thing here. Okay, so let me just print this as well. Right, so this were the initial weight I missed. I want to also see the uh, updated weights. All right, let me run this again. Okay, you can see that weight updation happens, right? Initial values of weights are 0.47 randomly picked up, right? Positive as well as negative numbers picked up. After the 1000 iterations, 10,000 iterations, you can see that weights are updated in this fashion. And important thing is, what is this? You see, you are printing your classified output. So let's quickly go back and see, right? What were the expected output? Expected outputs were 0, 0, 1, 1, because we are giving the inputs in the same order for a testing purpose. So I am expecting outputs 0, 0 saying that class 0, class 0, 1, 1. You see, it's a sigmoid continuous function, so you get real values as an output. Okay, so you see, first value is 0.01, close to 0. Second value 0.008, close to 0. Third value is expected 1, you get 0.9932. And the last value is also 0.9916. So pretty much close. You can use another function to truncate this, right? Like rint, which will make an approximation to the nearest integer, right? Rint you can use, or seal, or whatever, right? You can think of that, and you can update if you want exact answers like 0011, but I'm fine with this, right? So thing to remember from this is that this is the normal and the most simple way of, right, learning how the weight updation happens using a specific algorithm, right? In this case, it's delta learning rule. So you can see that, right, the delta learning rule has 3 equations, 2 runs. So I should write the code corresponding to that. That's what happens in this, right? So all the 3 equations we can see here have been implemented over here, right? pretty straightforward, right? Even when I write a code by myself, right, sometimes the mistakes will happen. My equation will be fine. Okay, I'm using the equation in a very proper way. But what I observe is that matrix dimensions do not match. So one important thing that I observed here is, it was my mistake, maybe to the previous batch or before that, right? So I didn't take this transpose because matrix was kept like this. I couldn't multiply. So it was giving an error when you actually multiply inside this. You see, you call the np.matmul here, right? That's one thing possible, right? I just have to trace back because inside this, if somebody throws an error, it is too hard to identify what exactly is happening because none of these variables, sorry, because none of these variables are available for us outside the function. So it becomes difficult to trace it out. This is what is a feedback that I give you, all right, when you write a code like this, right? So I think this is pretty straightforward, but still, if you have any doubt, please let me know. I'll try to clear that now itself before we go ahead. Any doubt? All right, let's proceed further. So the next thing that I want to discuss here is an example that is corresponding to. Okay, I'll write like this. Programming example for the batch method. All right, so directly we'll start. We directly, I think we have the sigmoid function already defined, so I don't want to start from there. I want to start from here. Okay, this is what is my objective now. I want to write a function that implements the batch method. So try to recall what is batch. I'll show you. Right. So you have to wait until the complete data set is used for training once. So once it is done, every time you might have calculated the delta W values, keep accumulating them in a variable, keep on adding them. Once, so in our case, we have only four samples in our data set. So wait until all the four of them have been used for training. Every time you use for training and calculate the output, right? You keep track of what is the delta W values, but don't use it for training. Keep accumulating them. Once all the four over, right? Take an average and use that average for the updation of the weight. Pretty simple, right? Okay, we are going to use that. All right, so let me call, okay, let's define a function. All right, so define, it's the same delta learning rule, but the scheme I'm going to use is a batch. All right, so delta learning rule using a batch technique, I should be able to get the values for W, then I should be able to get for X and T, right? So these are the three parameters I'm going to pass. All right, so yeah, so actually you see, this particular code worked with the 0.9, right? So I just wanted to talk about that. Sorry, I missed that other time. So the concept is like that. So data set is very simple, right? And even though you have the number of iterations like 10,000 and all, right? This higher value still works, okay? But if at all I say that my data set is a complicated image data set, right? I want to classify, say, 4 or 5 objects, or handwriting recognition, like 0 to 9 letters I write. My image size is say 1000 into 1000, right? It's a complicated data set. Then this 0.9 will not work, right? Even if you give 5 lakh, 10 lakh iterations, right? You call it, it will not, right? So you have to reduce that because there are so many things to learn. Okay, so you will get adjusted to this. You will be able to guess this when you do a lot of coding, right? So fine. Okay, so we came to here. Now my objective is to start with alpha. So I just remember that I should talk about the alpha. So alpha, right? Again, this is the same problem. So I still want to go with the same number. Let's see what happens. All right. So now, in this case, my approach should be different because I have to hold the sum of the dw value. Okay, so I'll call that as dw maybe sum. All right, so I have dw's coming for three different weights. First weight will get its own dw, second one its own dw, third is another dw. That should be taken for sum. Okay, so what we can do, I'll allocate the values. So np dot to create zeros of, specify the size, 3 rows, 1 column. Okay, there will be a single column, and this is a single matrix, column matrix. First value holds the sum of the first weight, right? Second one for the second, third one for third. It's a dw. Change in the weights for 4 times I run one iteration, one epoch. 4 times I get that dw value. So that should be taken as a sum and saved it here. Okay, so that's the purpose why I'm doing this. This is not there in the previous case. Then I need the n value as well. So I know that n equal to 4 in this case. So everything we have, directly let's jump to the training part. So I can start with the for. So for, this is the same as a previous case. Okay, so I in the range, say capital N. So do the same job, right? I keep writing, just see what I'm doing and understand. Previously we have done this. Okay, so this is x of I, comma, all the columns. Take one by one row from that x, and I also need the d value, right? The desired value from corresponding to this input is what I'm looking for. So this is d of I can write I. Okay, after that we have okay, I will get a v directly by multiplication. So np dot oh, it's, I think, mat mul. Let me check. Yeah, mat mul. All right, mat mul w comma x. Right, I get a partial output v. Pass this v through the sigmoid function to get a y. Y is equal to my sigmoid of this v. Right, I got a y. Now I need to decide whether I should go for a training. I should calculate the change in the weights or not. You do that, you can do that by checking this, taking a difference. All right, so call it as an error. Error is equal to d minus y. Okay, that calculates this. Then good to go for the delta. Everything you calculate, but don't update the weight. That's all. Okay. So delta is equal to what should be the delta? It's a phi of v into 1 minus phi of v, right? So phi of v is y. Okay, y into, this is 1 minus y. Okay, multiply that with the error. Okay, that's what is the delta value. Using the delta, calculate the dw as well. So keep everything, calculate everything. All right, so dw is equal to recall the equation. Yeah, dw is equal to alpha into delta into x, right? So okay, so that is alpha into delta, which is calculated, into the x, which is the input, right? Now, so we have the dw's, right? I'll try to write the dw sum here. I have to update the dw sum. Okay, so that is dw sum of the first value, it's a 0, is equal to, or I can use the, it's equal to here. Okay, so that is whatever dw we calculated, so that is dw of the first value. So dw sum of 0 value is equal to dw of first value, whatever we get as a dw in this previous case. Okay, and dw sum of 1 plus equal to dw of 1 and dw sum of 2 is equal to dw of 2. So dw sum gets adding how many times? 4 times. So we have the final dw sums over there. I need to take its average, correct? So let me go for an average here. So dw average. You see, I'm writing this outside the form because once all the 4 uh, values have been passed to the machine and machine has calculated the dw sum of each of the weights, I'll come out of that and I'll do this. So dw average is equal to, how do you calculate? It's a sum, dw sum which you have calculated. Simply divide that by n. N is 4, so it will get divided by 4. Now you update your weights. Okay, so let's update the weight. So that is w is my value. So you see w will be actually, from this we can see, you see w is equal to, w is this one I'm talking about, right? If I write w of 0, right, that will access this whole thing because that's the first element inside this list. It's a list of lists actually. It has taken in that way. So I should see this and then only I'll be able to judge what I'm supposed to write a code as. So the first element, if you want to update, this is not w of 0, it is w of 0, 0. In 0, you go to the first one. In 0, you go to the second one. That is w of 0, 1. Then this is w of 0, 2. So that's the only way to access that because right, we never did anything. We never said anything like specifically I want this format. So because the weights are present in the same format, I should update only in that way. There is no shorthand notation for that. So I should write this w of 0, 0, right, equal to, now you see what you want to update. Okay, it's not equal to, it's plus equal to d, I think dw, the average, right? I'll write 0. Let's see. I'm thinking that this dw average comes in the normal list form. I can access with 0, 1, 2 index values. Okay. If it throws an error, we'll see what should be done at a later stage. Okay. So next is w of 0, 1. All right. So this is plus equal to dw average of the next value, then w of 0 and 2 plus equal to dw average of 2. Okay, that finishes. We are still inside the function. Okay, I can return. Not, sorry, it's a w. All right, so w gets calculated like this, and we will be able to return this, right? Okay, so that's the function for this, and okay, I think I can use a part of this as it is. Okay, so I'll directly till here. I think I can copy. Okay, that's my main the testing function as well as the training function. Okay, so till here it is done. Now what I do, we have the values. Okay, directly go for epoch. All right, so for epoch in range, I'll keep the same number, right? Because maybe I will be able to make a comparison. Okay, sorry. What I want to do, I want to update the weight. Updated weight w is equal to, call the function. I think we gave a name, delta batch. So yeah, delta batch of w comma x input d desired. So that happens and we get the updated weight. So what I do, I'll also print the updated weights over here. Updated weights equal to this. All right, once that is done, I can go for a testing phase, right, wherein I think I should be able to do the same thing. Okay, n equal to 4, y is there. I pass, I call a loop 4 times. X will call. Okay, there is no desire now because whatever you get itself will be compared with the desired. So D is not required. right? Here I need a D. Okay, so let's see whether this is going to run. Okay, yeah, so clearly there is some difference. Okay, the number of iterations same, the number of times what you call, or the alpha value is also same, right? Pretty much everything is same, right? Maybe the initial values of the weights will be different over here, right? That as of now we cannot do anything about it, right? So right, we initialize with the random weights, fine, but you see, right, this is the initial weight, this is the updated weight, there we can see a change, and also we can see that, right, the values are close enough but not as close as the SGD technique, right? Because there you were updating for every epoch, for every instant of train, right? But here you are not doing that, right? So because of that, it's clear from this result, it's not the same result as this. You see here, this was 0.0101. So you see here, this is 0.02. This is actually not close to zero. You can say there is a slightly more error, right, with this. That's what is the conclusion we can derive. So 0.008, right? So this is 0.016, almost double, right? The next value 0.9932, 0.9863, right? So anyway, in order to make a decision, no problem, right? If you use a rint function or something, np.rint of this, it will directly give you 0011. Absolutely fine, no issues. Okay, so classification happens, everything is fine, right? Then the last number, if you want to compare, this is 0.9916. We are comparing that with 0.9830, which says that okay, right? So as of now, what we can conclude here is that, right, so weight updation happens, right, using various schemes possible. The third scheme, which is mini batch, again, so you know how to code now. So that part I'm not going to write a code from scratch in the class. Okay, that's going to take some time. We'll go further. Okay, during that time we can go and discuss something ahead of that, and that part will be another homework for you. All right, so please take some time to understand that and write a code. Take a mini batch size, fix it. Like in this case, you can take mini batch size as 2, right? And again, that's a suggestion, because 1 is already done, which is the SGD. 4 is also done, which is this case, right? Maybe you can think of how to write a code for the mini batch size. You define your own size, all right, and try to write that. Okay, so do that work, right? Those who get any doubt in that, I'm there to help. All right, okay, so that comes to the end of today's session, right? And if you have any doubt, you are free to ask.
So there is no doubt, but like, okay, if we change the range for a epoch, which is like, okay, now we are saying like, okay, 10,000.
Yeah.
Instead of that, if we do it 20,000, this accuracy might.
Yeah. I will show you. I'll show you. Since you asked that doubt, I'll just do that. Right. Slight change is expected. All right. So some change, right? So more learning is there. So the solution is that, okay, if you want to go for this technique, maybe the number of epochs to be increased, right? So that's what is the conclusion that we can draw here. Let me show the other value as well. Let's go for a bigger number. Let me make it 50,000. All right. Now I am expecting pretty much closer answer. Okay, whatever we got earlier, like 0.99, 0.99 in the cases, I can expect that, because you are doing more learning here. It's going to take little bit more time, because maybe 4 or 5 seconds maybe. All right, but you can see, right, that's what I'm expecting. Answer coming closer to that. Yes, you see, 0.009, 0.007, 0.9939, 0.9925. Yes, so you can derive a lot of conclusion from this. Right?
Yeah, thank you.
Yes. Any other doubt? Anything to discuss?
Sir, we are giving input row-wise or column-wise here?
Row-wise. You see?
Row-wise. So here are the 4 rows. Yes.
Yes.
And the weights are 3. So we have skipped one row or what?
No. You see, every row has 3 elements, right? I am taking a row, but when it goes into the machine, it becomes like this. You see, 0, 0, 1, 3 weights.
3 weights only?
3 weights, right? Because each row, inside the row, I have 3 elements, right?
Okay.
I'm passing the row at a time, but row will not go like this. Row will go like this, right? Because 0, 0, 1 will go into this. I have W1, W2, W3. 3 weights corresponding to 3 inputs. So
in the
okay,
so
don't
in
get
this
confused.
case,
Yeah. Please hold on.
Yeah, so-
Nitin, I'll just answer.
no, yeah.
Okay, yeah. Jyoti,
I was
clear?
just
No, he's asking about this question.
Same
only.
thing. Okay, yeah. Please go ahead, Nitin.
Yes.
Yeah, so what I was saying, this basically weights are equal to the like, okay, number of weights are equal to the number of x columns.
X values, right? Correct. Columns. You see
Columns.
this one, right?
Yeah.
So 0 is x1, next 0 is x2, 1 is x3. Corresponding to these 3 points, I have W1, W2, W3. 3 weights. Is that okay?
Yeah.
Okay. Yeah. Please go ahead. Any other question? Okay, so we have come to the end of today's session, and tomorrow's session will begin from here. I'll try to write a code which gives you a clear-cut idea that how much error is present per epoch. Whenever we go through epochs, how much error is present when you use SGD and when you use batch, right? We'll try to write a hybrid code which uses both of them together, and we'll try to visualize something. Okay, so that gives you more idea about which one is better here. Okay, for a given number of epochs, right, which one I should choose, right? That gives you an idea about that. Then tomorrow we have many other important topics to learn like this. From scratch only we'll do that. We'll even study the back propagation, how the error is propagating back. We'll visualize that. What are the problems associated with them and how to overcome that, right? Major issues will be discussed there. Again, I'll try to teach in the scratch level only, not using the built-in function. Okay, so once we are comfortable with all these concepts, definitely we can go ahead and use the built-in functions at a later stage.